so last lecture we looked at the concept of overfitting, where we pick too many neurons in the hidden layer as an example, and it overfits the data. How can we prevent overfitting? One technique, if you recall, was regularization, where in the loss function we add the square of the weights. So if the square of the weights gets less, the loss function improves. So this leads to smaller weights. Smaller weights help us against overfitting generally. Another technique we discussed in the last lecture was dropout, if you recall, where randomly we select some of the neurons in the hidden layer, we zero them out, and so that the other neurons learn to compensate for some of the missing neurons, so that also helps against overfitting. Okay, and again, there's another technique called early stopping, where if we are going through and training through too many epochs, okay, so for example, if every epoch, if we had, for example, a validation set, see, typically whatever data we have, we divide it into three categories: training, validation, and test. So for example, let's say we have 60,000 data available to us to be able to train, right? Let's say we have 10,000 separate data, so that we do not show this to our neural network. Once it's trained, then we will verify to see what's the performance on the test data. So then what we can do is break this 60,000 into, let's say, 50,000 for training and 10,000 for validation. So this 60,000 gets broken into, so at the end of every epoch, we test it on the validation set, right? And if the validation accuracy keeps getting better, right? So in the beginning, accuracy will be low. As we go along, it will finally start to saturate. And if we overtrain, it might even drop down. So we can basically keep track of it, the validation accuracy in every epoch, and stop, right? So suppose this is 30 epochs, this is 40 epochs. So this is what's called early stopping, and that also helps against overfitting, because if we keep training more and more, even though our training loss will keep getting better, but that doesn't necessarily mean it will do a good job on the real test data, right? So anyway, we discussed some of these options, and another thing that we discussed was last several lectures. Okay, let's say we are creating a neural network, right? Okay, our input size is not in our control. So for example, if we are doing MNIST digit recognition, okay, 28 by 28 pixels, which if we flatten it out, comes out to 784 by 1, is our input size, right? So our input size for MNIST will be 784 by 1, right? So then in the hidden layer, suppose we decide to use 200 neurons. Okay, so this is flexible. We can play with this number. If we use too many neurons in the hidden layer, it will overfit. If we use too few neurons, it will underfit, right? And very similarly, the output neurons for the MNIST digit recognition, how many output neurons do we have? 10, right? So this has to be 10. So once again, this is fixed because it depends on the problem that's given to us. The input is fixed. So input is fixed from a size point of view, right? So that depends on like 784 in this case, but this is flexible. This is what we can play with and see what will be the optimal number that will give us the best accuracy, right? Okay, so now in the MNIST data set, as I had mentioned to you, and I think in your current assignment, you're also working on it. In the MNIST data set, we have, once again, 60,000 training, which you can further split into training and validation, just like I discussed, 50, 10, you can split. And we have 10,000 sample digits for testing. Okay, now on your laptops, as I mentioned, if you train it on the entire 60,000, it may take a while, right? So that we can understand the concept. So in your current assignment, what I did is gave you a subset of this, which was only 1,000 total digits, 10, roughly 100 of each category, like 100 twos, 100 threes, and so on. So if you now, let's say, created a neural network with 784 by 1 inputs, 200 neurons, 10 neurons, and you trained it only on the 1,000 training set, the subset that I've given you, okay? If any one of you have already attempted it, you will notice is the best accuracy that you will get. So accuracy that you will get on the full 10,000 test. So you train on 1,000 and you test it on the entire 10,000, right? Best accuracy you will get will be around 90%, okay, which is relatively low. If you trained on an entire 60,000, then you might get 97, 98% accuracy. Okay, so my question is, if let's say this was the case, we only have 1,000 data points. Okay, we wanted to improve this accuracy. So let me propose a solution to you and see if you guys agree. So if we wanted to improve the accuracy with 1,000 training and input data, okay, what if we do this? Okay, we add one more layer over here. Let's say 500 neurons. Okay, and our input will be 784 by 1. So in other words, what I'm saying is add one more layer. So there are 2 hidden layers. Will this give us better accuracy? If we use 1,000 for training, tested on the full 10,000, will it give us better accuracy? What's your guess?
Maybe do so, because more classification maybe.
Does, okay, let's go back to our fundamental concept. Just adding hidden layers, does it help with the accuracy? No. So in fact, in this case, it will severely overfit the model.
Because you have more parameters.
More parameters, and our training data is far less. Okay, so as a general rule, your training data has to be far greater than the number of parameters, which is weights and biases, total weights and biases, right? So this one will not work. Okay, what if somebody says, no, you have to do something, your job relies on it, or you may not have your job. How would we make it better? Okay.
Can we create the more data, like randomly?
Suppose that's also out of the question. This is all the data you have, only 1,000. Okay. So let me give you a few ideas. Okay, one possibility would be, okay, if you take a look at any digit, right, 28 by 28 pixels, and if you try to view it, what you will notice is this one appears in white color, and the background is black. So a black color in the background has a pixel value of 0, right? only where the digit is, you will have close to 255 for the pixel value, right? Very similarly, if you have a 3, what I'm trying to say is, whatever pixels are over here, do they matter
No, no,
in digit recognition?
no.
Absolutely not. So why are we making it unnecessary worry about all the background? Okay, and that's the part of the reason for low accuracy. Okay, if somehow we can teach it to ignore the background and focus on the digits, then perhaps it will improve accuracy, right? So I'll show you 2 techniques today, which will help us in that direction. In your next assignment, you will try it yourself and verify that it indeed is the case. So one possibility is, okay, what we do is, okay, let me put some kind of a pre-processing. And the goal of this pre-processing would be to de-emphasize the background, okay? So it will output 200 over here, as you can see, right? On the input, it will do, again, 784 by 1. Okay, so again, if somehow, once again, we come up with pre-processing to, okay, so goal is to enhance important information in input data. Okay, and de-emphasize, meaning don't pay much attention to, the background pixels, if we can do that. So I will show you 2 techniques today, which will help us in that direction. One is a classical technique. Some of you have seen it in computer vision or some other courses. So one technique is called principal component analysis, PCA. Okay, so first, as I describe what PCA is, the mathematical concept, then I will provide you all the code, then you will try that and see whether it improves it or not, right? So this stands for principal component analysis. And I'll go into the mathematical motivation behind it, why it works. Okay, then what we'll do is we'll replace PCA with a better neural network based equivalent. So replace PCA with better neural network based equivalent. So again, this pre-processing then will become another neural network. So even though in the end it will appear like a hidden layer, but its job is really to do some kind of enhancement of the important information. So because we will train it in a very special way, you will see it will end up improving the overall accuracy of our system, right? So the 2 techniques for pre-processing so that our overall accuracy improves. Okay, let me start first with PCA, then I'll show you what is a better way to do the PCA in the deep learning world. And then your new assignment, once again, will be based on this concept. Okay, so now let me go into a quick summary of the PCA. If you're taking the computer vision course, you'll be programming it from scratch. But here I will give you a library that will do the PCA. However, briefly I'll explain the mathematical reasoning behind it. So PCA. So first of all, goal is dimensionality reduction. Okay, for example, let's take a look at our MNIST example. Okay, every MNIST digit, as we discussed, is 28 by 28, right? If we linearize it into a vector, this becomes 784 by 1. So as we have discussed before, you can think of this, each digit, as one point in 784 dimensional space. You know, just like we discussed, let's say I have x, y, z axis. If I have one point, let's say x of 2, y of 3, z of 5, right? I could represent it as a vector, 2, 3, 5. So as a 3 by 1 vector. Very similarly, if I have a 4-dimensional space, I can represent each point as a 4 by 1 vector. Similarly, this digit, which is 784 by 1, can be thought of as a single point in 784 dimensional space. Okay, so what the PCA is going to do is reduce these 784 dimensions. So if we apply PCA, it will reduce the dimensions to, for example, 200 dimensions. And we will be able to pick how many dimensions we want to reduce. So from 784, we can reduce to 200 dimensions. So in other words, each data point or each digit, which was 784 by 1, as we apply PCA to it, it will simply become a 200 by 1 vector, right? However, the 200 numbers that we were reducing the 784 from, we want to pick it in such a way that it keeps the most important information in the data. So we cannot manually go and say, okay, pick this one, pick this one, pick this one, right? Because somebody else may have a 2 which is off-centered. So you cannot manually identify the location of the pixel. Okay, so we have to do it in an automated way so that from the data it is able to pick the most significant 200 numbers that need to be preserved. Then we can pass this 200 to the hidden layer in the output layer for classification. Okay, so now let me go to a little bit of the math behind it.
They also should be in specific order, right? Since
Order doesn't matter.
doesn't matter.
Yeah. Is there another question? No. Okay. Okay. So anyway, so now let's go into a little bit of the procedure. Then we'll take a look at the intuition behind the idea, understand it, why it works. Okay. So let's pick an example. Suppose in our case we have 1,000 test data. Okay, before I go further into the details of the PCA, keep in mind PCA is an unsupervised learning technique. Okay, what's the difference between supervised learning and unsupervised learning? What we mean over here is in supervised learning. So over here.
We have this.
So in supervised learning, okay, we have to indicate which class data belongs to. So as we train the network, for example, if we have a 2, we have to tell the network during training that this is the digit 2. Very similarly, if this is the digit 5, we have to tell the network it's digit 5. So that's supervised, right? The category or the class the data belongs to have to be indicated to the system that we are creating, to the network we are creating. In unsupervised, we just give it the data. We don't tell it whether it's a 2 or a 5, it doesn't care, okay? From the data, it will automatically learn what is important, what is not important. So that's the beauty of it, right? Okay, so now let's come and take a look at the procedure for PCA. So the procedure goes something like this. Suppose we have 1,000 test data. So in this case, these are the digits, right? Sorry, I shouldn't say test, these are the training data. Okay, so we have 1,000 training data. These are the digits. Each is 784 by 1, right? So first thing we will do is assemble it into, or I should say, assemble training data into a matrix. Okay, so if I go, I put 784 by 1, so this is digit 1. Then very similarly, the second digit in our training, the 784 points over there. I'm just putting them side by side, okay? So suppose I call this my input data. So I call this the I matrix. So this is the input data. Okay. What will be the size of this matrix?
784 times 10. That's
784 by 1,000. Okay, so then what we do is, so then typically we mean adjust the data. Okay, so what we do is we go to every row. How many numbers are inside each row? 1,000, right? We take the average and we come up with the mean vector over here. So mean vector, as you can see, will be 1,000 by 1. Sorry, 784 by 1. Okay, suppose I call this mu. Once again, how do we get the mu vector? We added every row, all the numbers. There will be total 1,000, we divide by 1,000. Same way we go to the second row, we add, divide by 1,000. So as you can see, the mean vector will still be, there are 784 rows, it will be 784. Okay. So once we have computed the mean vector, then we will say, let's say, I hat or whatever tilde equal to I minus mu. So we subtract this mean from every column over here. So this is the mean adjusted data. So this I hat over here, or I tilde, is the mean adjusted data. Okay, so let's try to intuitively understand why are we doing this. Okay, suppose in a high dimensional space, we have some data. Here's one data, here's another data, here's another data, right? Okay, if we take the mean of all of these numbers in this two-dimensional space, wouldn't the mean appear somewhere? Wouldn't the mean appear somewhere, you know, whatever, so this would be the mean, everybody agrees? Somewhere in the middle, right? What if I, from every data point, I subtract the mean? What will it do to the data?
Do we move it to origin?
It will shift the whole thing to the origin. So that's what we are doing. Essentially, if we subtract the mean, everything will be centered around the origin. So all of our data. So which makes sense, because why have the effect of the bias on our data? So anyway, so that's pretty easy. So then what we do is we try to see what is the relationship of each data to each other. for example, as you can easily see, the 2s that we have are correlated with each other, right? The 3s have a more relationship with another 3, but not with a 7 or 6 or whatever. So next thing we do is we create what we call the covariance matrix. So covariance matrix is created simply as I tilde, which in this case will be, see, this will still be 784 by 1,000, correct? So if I took the transpose of it, multiply it by the mean adjusted image, what will be the size of this covariance matrix? Won't it be 1,000 by 1,000? Right? Because remember, if I took the transpose, this becomes 1,000 by 784. So this is 1,000 by 784, and this is 784 by 1,000. So we'll be left with 1,000 by 1,000, right? So intuitively, what you can see is as we multiply these two, so this 1,000 by 1,000, okay. So essentially, this is basically I0 tilde prime times I0 tilde. Then the next value is I0 tilde transpose times I1, and so on. So basically, so if I0 is our first, so first thing over here is I0, this is I1, this is I999 in our case, right? So essentially what the covariance matrix is doing is saying, okay, what's the relationship of this data with itself? Then what's the relation of this data with the next data? This data with the next data. So it's looking at all possible 2 at a time relationship between, you know, and the last entry over here, as you can see, will be I0 tilde transpose times I99 tilde, right? And same way, this will start with I1 transpose times I0, and so on. Okay, so keep in mind this dot that I wrote over here, I0 times I0. This is what we call the inner product. So it's just a scalar. Okay, often we write it as I0, I0. So this is how mathematically we express the inner product. So essentially we are doing the inner product of every data with respect to every other data. Okay. If the 2 are very similar, what will happen is they will end up producing high number. Okay. So anyway, once we have created the covariance matrix, then our next step is compute eigenvalues, eigenvectors of the covariance matrix. Okay, so if you have forgotten what is eigenvalue, eigenvector, you know, you guys can look up Wikipedia, get a quick refresher on. But essentially, let me give you a general idea. The eigenvalue is computed as the determinant of lambda I minus A. So I is the identity matrix, lambda is what we call the eigenvalue, A is the matrix that we are trying to compute the eigenvalues for. Anyway, there's a standard procedure, you guys can review it and figure that out. Okay, For right now, what's important to know is if you have a 1,000 by 1,000 matrix, it will produce 1,000 eigenvalues. If you have a 200 by 200 matrix, how many eigenvalues will it produce? 200, right? Corresponding to every eigenvalue. So corresponding to every eigenvalue, there is an eigenvector. Okay, corresponding to every eigenvalue, there is an eigenvector, right? Okay, so in this example, as we discussed, there will be 1,000 eigenvalues. There will be 1,000 eigenvectors. Each vector will be 1,000 by 1. So each 1,000 by 1. Okay, so now suppose our goal was that we wanted to reduce the 784. So let me go back to my original goal. The original goal was we are given 784 dimensional space. We wanted to reduce it to 200 dimensional space. Suppose that was the goal. Okay, so so these eigenvalues and eigenvectors now, as you will see, will help us achieve that, right? Because our goal is to reduce it to 200 dimensions. How many eigenvalues did we get? 1,000. If the goal is to reduce it to 200, that means what we need to do is pick 200 of these and ignore the other. Okay, but the question is, should we randomly pick 200 of these, ignore the other? We want to pick those which have the highest information, okay? So the highest information is in that data which has the highest eigenvalue, okay? So the way we do it is we sort eigenvalues, okay? Then pick 200 highest of these, not just randomly the top 200, and ignore the other 800 because they have less information. Okay, so then corresponding to those 200 eigenvalues, we will create the eigenvectors. So eigenvectors for these top 200 eigenvalues. Sushant, if you can make sure, is this part covered?
Yes.
Okay, just wanted to make sure. Okay, so now let me ask you, if I put those eigenvectors side by side, what will be the size of this matrix? What was each eigenvector that we obtained?